Hi, my name is Scott Simpson, and today we're going to be talking about free energy and its relationship to cell potentials. So the Gibbs free energy is related to cell potentials and the transfer of electrons, which means if it's connected to free energy, it's also connected to the equilibrium constant. So let's find out what the connection between all of these things are. So the electromotive force, which is related to the cell potential, the electromotive force of our cell potential is related to delta G by the following reaction, where we have delta G is equal to, and what this is the maximum work that you can get out of the system, but negative NF times the electromotive force, E. So again, let's describe what each of these things are. N, that's the number of electrons. Let's see if we can see that. We might turn that up a little bit. There we go. That's a little bit better. Is the number of electrons, and these specifically the moles of electrons that are being transferred, or that stoichiometric coefficient. We have F, which is Faraday's constant. So they spell it. Yeah. Which is equal, 1 Faraday is related to coulombs. So it's 96,485 coulombs per mole of electrons. And it's also related to a joule mole times moles, whichever way you want it to be expressed. They all mean the same thing. Okay. So this is at non-standard conditions. At standard conditions, delta G is going to switch to a delta G naught. We still keep our N, Faraday's constant, and then we have E naught, where E naught is going to be of our cells. So let's ask a couple of questions before we go further associated with this. So the question that we're going to ask is, see, I might need to go a little bit lower so this thing's in that way. What does the sign of E naught have to be to make sure the process is spontaneous? Question: what is the sign of E naught for a spontaneous process? Okay, so for a spontaneous process, we want the value of G to be less than 1. Want it to be negative. Delta G needs to be less than 0. Looking back at our relationships then, if we want this expression, this term right here, to be 0, this has to be a positive value. So E has to be greater than 0. Cannot be a negative. In the case of standard conditions, looking at that, that must be true. Okay, so I said it earlier, since we're talking about a delta G, we can actually link that delta G to an electromotive force, and we can get that delta G connected to an equilibrium constant. So we can link our standard electromotive force, E naught, to the equilibrium constant. So we previously said if we're looking at the Gibbs free energy under standard conditions, we just have to take negative moles of electrons transferred times Faraday's constant. And that electromotive force under standard conditions, or E cell in some case, we know that that is true. Also, we have previously derived a relationship where delta G naught is equal to negative RT ln of K, the equilibrium constant. Now, if we set these two terms equal to one another, and we box out the delta G, we can say that negative NF E naught is equal to negative RT ln K. If we want to isolate K by itself, what we have to do is move the negative RT over. So we get NF E naught over RT. And our negatives cancel out because we just moved them over to the other side, is equal to ln of the equilibrium constant. Great. So we have this as an expression. Now, if we want to isolate K by itself, what we have to do is raise everything to the power of E. So K is equal to NF E naught over RT. So that's where we have a relationship. Let's look at an example utilizing this information. Okay. To do so, we're going to consider a galvanic cell, a battery, and it's going to be an iodine copper battery. And what we're going to try to do is calculate the equilibrium constant associated with it. So we're going to be utilizing these equations in a moment, but let's write out our question. Okay, so let's try to do it again. So example, what is the equilibrium constant for, yes, an iodine copper 2+ battery? First thing we need to do is look up the standard production potentials of these guys. We also know our chemical reaction that we're going to have based upon those standard production potentials. If we look those values up, we have one that's more negative compared to the other. So we can tell what's going to be oxidized, what's going to be reduced there. So if we look up coppers, we're going to consider the copper going into copper 2 plus 2 electrons, and E naught for that is equal to negative 0.34 volts. And then if we consider another standard reduction potential that we can look up, I2 goes to negative. E naught from this system ends up being positive 0.54 volts. Now again, I'm a chemist who tends to, when you flip these, you change the sign of them. Some people don't do that, so their definition of how to calculate E naught of a cell changes. In some cases, they like to just subtract what they have E cathode minus E anode. I prefer not to do it that way. I generally just take what I have here after modifying and flipping equations and add those two things together. So we want to calculate E naught of our cell. So we take E naught cathode plus E naught anode. So we're just going to slap these two things together. And what that will get us as we do that, so we get 4 volts. Since we have these two, we're going to subtract off this guy. When everything's said and done, we end up with 0.20 volts. Okay, based upon this, we know we have a positive E naught of our cell, which means this reaction is going to be spontaneous. If we calculate the equilibrium constant, if it is spontaneous, the K value should be greater than 1. Okay, now what we have to do, we have to calculate K. K is equal to E raised to the power of N F E naught over R T. Okay, we can plug all these values in, and we have to keep track of the number of electrons that are being transferred. From our half cells, we know that this is 2. So we got E. Let's switch over. There we go. E, 2 times our Faraday's constant, 96.485. We're going to use joule per volt times mole. This technically is a unitless parameter, which we'll see in a minute. We have our cell potential that we just calculated. Divided by, we have our ideal gas constant, 8.314 joules per mole times Kelvin. And then we have the temperature at which we're operating at. It wasn't explicitly stated, so we assume 25 degrees C or 298 K. When you multiply everything through, you should get a value of 5.8282 times 10 to the 6th. Showing that in this case, we do in fact get a value greater than 1, which is what we expected for the spontaneous process. All right, with that, we talked about the connection between delta G, the equilibrium constant, and the standard cell reduction potential. We went through an example of how to calculate that. If you have any questions or comments, please leave them below. Thank you for your time. Have a good day.